Hi, everyone can hear me? Okay, awesome. Really happy to be here. So before I dive into enterprise AI stuff, I want to take a quick detour to the world of cars. Not the automated kind that we find in the literature that we read about on a daily basis nowadays, but the kind that still dominate our cities. We've, as a species, we've faced many times before this challenge of building massified, trustworthy, yet potentially very dangerous technologies. So if we look across to some of those other sectors, like what can we learn from the experience? The first, obviously, is that cars are made from an extraordinary number of components, but not all those components have an equal weight when it comes to driving the core metrics of reliability, robustness, safety, security. Remove the engine. This is an old engine block. Remove that engine from the car, and the car simply won't move. It's almost not a car anymore. The door, by contrast, is not providing any kind of mobility service, but it is providing safety, security, comfort services to the passenger. You can't confuse the vehicle with the engine, obviously. Like that seems like a common sense thing to say. You can test an engine all day. It's going to tell you a lot about horsepower, efficiency, responsiveness, maybe the likelihood that the engine can catch fire on its own. But it's not going to tell you much about the overall trustworthiness, safety, security of being in a vehicle. Crashworthiness, visibility from within, visibility from outside, if people can see you when you're driving at night. The responsiveness of the steering wheel. All of these things that really, really matter for safety and security of the technology and that ultimately drive trustworthiness are not going to be things that you learn when you're testing on the engine block. But beyond that, there's an extraordinary number of safety and security pieces that are actually elsewhere in the car, right? The airbags, the seat belts, the crumple zones, and so on and so forth, and more of these things with IoT that's being implanted into cars. And it goes well beyond that into the environment, right? We've designed cities, roads, social systems, training, education, standards, policies, laws, all of which shape behavior of drivers, pedestrians, cyclists, and so on in a way that encourages the trustworthy use of that technology. And beyond that, again, there's the factory floor. Right, there's a tremendous amount of aspects of the production of vehicles that have to do with how people behave when they're producing those vehicles. This is an andon cord, which famously inside manufacturing plant is there in case people see something that's gone wrong and they want to immediately halt the production site so people can come and talk about what went wrong and see if something needs to be fixed. But there's lots of other things as well that shape the way that people behave on the production floor that have been kind of ingrained into it so that car companies and car piece companies can manufacture at scale, reliably and consistently in a way that produces trustworthy vehicles. So all of that pushes us to have a mentality shift about how trustworthy technology gets produced. Frequently, the conversation is dominated by conversations around safety and security of models in the AI space, which is a little bit like thinking that the safety and security of people driving and pedestrians around cars should be judged by the testing that's done on the engine block. And we know that absolutely is not the case. This is, in case anyone's familiar with safety science, this is what we call the Swiss cheese model of risk reduction. Okay. The premise here is that an individual slice of Swiss cheese here basically represents some kind of a support or control or defense layer in your system. Every layer has holes, just like it does in a slice of Swiss cheese. But those stack layers together, and the holes are actually different for every slice of Swiss cheese. So the idea is that as hazards come through, most hazards are actually going to hit a piece of cheese. They're not going to be able to get through holes because the holes rarely penetrate the entire block of cheese. But in this case, you see that one of them actually did get through, and when a hazard gets through all holes in all the slices, we think of that as a failure. So what's key here is a couple of things. One is that the holes can be big or small. The holes move over time. So what was safe yesterday won't necessarily be safe tomorrow or even today. And also that the holes represent a couple of different things. One is a form of immediate or active failure. So imagine someone who makes a bad decision on the spot. Other things are more passive and latent conditions. So imagine how incentives are structured inside organizations, or imagine the user interface that's designed in a way that works really well in most situations, but that when combined with some kind of active failure that happens in the moment can create an overall failure of a system. So what's really key about this model is the importance of independence and diversity in your layers. If all your layers share the same assumptions, the likelihood that there are holes in the block of cheese that go all the way through is exacerbated enormously. By contrast, if you have layers that have been designed independently and that draw on just different philosophies of how you catch hazards that are coming through, some of them physical, some of them digital, some of them procedural, the likelihood that there are holes that actually penetrate the entire block of cheese is very low. So that model, let's think about it now in the context of another technology that is potentially very dangerous, lethal, aviation. How is it that we've come to be in a situation where we avoid almost always mid-air collisions between planes, despite the fact that they're taking off at an unbelievable rate from the large airports, taking off and landing? They're flying all over the place. There are different kinds of vehicles flying at different heights, and rarely is it the case that there's any collision between them. Well, this is Swiss cheese model in action. We've got rules and spacing. So this is a little bit like lane markers on roads for cars. Planes have, and pilots and ground crew and air traffic control people have this understanding and procedures and rules that maintain space between vehicles or between planes, and requires them to remain so far from each other when they're taking off, landing, and they're taxiing on tarmacs. Transponders, every plane has basically a tool that's emitting signal, that's giving a signal to other people, either air traffic controllers, other pilots, other people in other vehicles, a signal that tells them where they are, where they're headed, what their elevation is, and all of this. Procedures and communications have been standardized in a way that allows people from different countries, different places, different companies to talk with air traffic controllers and sometimes talk to other pilots in a way that doesn't create miscommunications or ambiguities. And that's all been drilled into the way people behave. Last resort, onboard computers. So there's a computer that's actually reading inside every plane and airborne vehicle. I'm imagining there's a computer that's reading the signals of the vehicle that it's inside, but also other vehicles from the transponder, and judging whether those vehicles are approaching one another at a rate that's dangerous. And if it reaches some threshold, it will give an automatic alert to the pilots to either raise or lower the vehicle. And finally, training and discipline. Pilots have been trained to always follow the advice or mandate that's been given to them from that computer. They've been trained in the procedures and communications that have been standardized and so on. So all of this is basically Swiss cheese model in action, right? You've got a variety of technical, socio-technical, procedural, legal layers that create a situation where the technology is trustworthy. People don't even think about safety and security for the most part when they get on planes these days, and it's because of this layered approach to trustworthiness that's been effective. So what's happening in AI? You don't have to be, you'd have to be asleep to not be hearing about all the data around AI adoption, right? ChatGPT, over 200 million weekly active users. That was from a couple of months ago now, I think. So God knows where we've gotten since then. Stack Overflow in their recent developer survey reports that over half of developers are using some form of AI coding tool in their daily work, which I think is actually an underreport, but anyway, it's still very high. That's professional developers. McKinsey reports that about 80% of large organizations have deployed AI tools in at least one use case, one major function inside the organization, with a number of them in more than one. And as you can see, these are hockey stick style curves. So like the number of organizations that are deploying in more than one, two, three functions, major functions within organizations is rising. And here we're talking about some of the largest organizations in the world. Okay, so maybe the trust problem is actually silently being solved, right? If everyone's adopting, it must mean that people trust the tools that they're adopting. And I don't think that's the case at all. First, again, if you're paying attention at all, you know that threats are dramatically on the rise, right? As systems and models are becoming more sophisticated and powerful, what it means is that the attackers have access to an array of tools that are miles ahead of what they had even in the recent past, and they're actively developing at a speed that is far outpacing the defenses that people are able to build. The use cases where we are seeing adoption tend to be low-risk use cases. They tend to be use cases where humans are absolutely in the loop all the time. So think about a tool where you and I are interacting directly, ChatGPT kind of discursive interaction flow. The human is very much in the loop and playing a role in deciding whether or not they're going to use the content. When enterprises are thinking about deploying into use cases where a lot more is on the line, and they're thinking about using generative AI for automation and expanding the range of autonomy of agentic flows that they're putting into place, it's a wildly different use case from you and I using ChatGPT to get answers or to help us with our research or anything like that. And so the risk level expands enormously. So you have attacks are growing in number and sophistication and speed. The systems we're deploying are growing in complexity as we're trying to enter into new use cases and leveraging different forms of context and memory engineering and guardrails and everything. The pieces are growing, which means that the attack surfaces are growing. The autonomy that we're trying to give to the systems is growing. All of this is creating a situation where there's a tremendous amount of concern inside organizations to deploy beyond where we've gotten today. There's still a lot of low-hanging fruit for deploying relatively simple, controlled, heavy human-in-the-loop kinds of tools, but beyond that, I think there's a lot of trust problems that simply haven't been solved in what we have today. Okay, and I think part of it is the model centricity problem that the field has. The public discussion, even a lot of the academic and industrial research, I think, is enormously dominated by discussions around whether models have progressed, whether models are safe, models are secure, models are trustworthy, and so on. When new models are released, everyone's looking at the evals and comparing models to previous versions or other models that are coming out at about the same time on public benchmarks. All that stuff is important. It's a kind of signal. But the importance of that in telling us whether that model deployed into a specific setting to do a specific thing with architectural components around it that were not involved in any of those evaluations is very low. It's quite possible for the same model deployed into different contexts and different architectural settings to have a dramatically different kind of risk profile or performance profile. So here's a really simple example. So this is password reset agent use case, okay? A very common use case inside enterprises for the company that I work with. And this is not reflective of anything that my company has worked on. This is really just an example that is here for the presentation. Two systems leveraging the exact same base model with very different architectures to try and solve the same problem. So you'll see in system A, we've got it pinned down to our workflow. There are identity checks, scope credentials, guardrails, human approval or human in the loop for specific high impact steps, telemetry to allow for auditing and perhaps some alert signals, kill switch, and so on. System B, by contrast, is a small model with good generic performance that's doing the heavy lifting, broad tool access, no gating. The model itself is doing a lot of the heavy work when it comes to responding or making decisions about what it should do to respond to a user query. Whereas in System A, the architecture is dramatically different. So same base model, opposite risk profile. In System A, the safety and security layers are outside the model in other components of the system architecture. Safety testing in AI is usually very generic, model-centric. We're talking about toxicity, bias, fairness, disinformation, self-harm, bomb plots, things like that. Okay, those harms can really matter in some contexts, but in the lion's share of actual enterprise deployments, these are not at all relevant risks to be testing for, right? So when people are doing so-called safety testing and reporting on model safety, keep in mind how little of the safety spectrum is actually being tested for and how irrelevant the safety risks that are being tested for are for most use cases that people want to be deploying these systems for are today. Like, context really, really matters. We need to be evaluating and building for the things that actually drive trust, as opposed to simply reproducing the kinds of evals that other people are doing, and you feel like you need to be part of the crowd and doing, evaluating on all the same public benchmarks. So here's the quick mapping I'm going to use for the rest of the talk. From the drawing on the car analogy, that engine block is the model. The vehicle is the AI system. In other words, the model coupled with things like your context management system, your memory management system, the prompt or prompts that you're using, and so on and so forth, guardrails that may be in the system. The roads and rules is the environment around it, so think standards, laws, training, certification, corporate governance policies, and so on, the things that shape behavior. And the factory is our production process. I'm going to talk about these two in particular for a couple of reasons. One, the model layer gets a lot of attention already. It's super important, but I'm just not going to dive into something that I think we deserve. The conversation needs to move away from a model-dominated situation. I'm not going to talk much about the environment, not because it's not important, but I think because it's dramatically underdeveloped right now, and also because this is a more technical audience, I think, judging from the way the event's described, and also who else is talking at the event. So I'm going to focus on how we do the production of the technical thing and what that technical architecture actually is. Okay, I'm going to focus, the first part of the talk, or the second third of the talk maybe, is going to be about this, what I call the runtime trust stack. I don't know why I keep using my keyboard instead of this thing, but okay, so a lot of categories of things that are at play here, okay? I'm not offering this up as a kind of canonical taxonomy of different components. I'm also not trying to suggest that this is comprehensive. We can debate about whether some of these things should be merged or whether there's too much in any one of these buckets. It's really just to put on the table the number diversity of buckets of tooling and components that are available for trust work when we're thinking about architectures. So from a reasoner perspective, right, this is where we have the opportunity to set the system's baseline error uncertainty. We can tame generation so that things downstream are easier for us to secure and verify. So we can pin versions, for example, make it much easier for us to roll back and understand what version was operating at any given time. We can decide on a conservative approach to decoding so that in particular for high impact steps, so that we can avoid situations where there's just too much stochastic behavior that's happening. We can prefer tool verified answers over free text, allowing the reasoning model itself to respond. From a planning perspective, we can impose pre and post conditions on different gates to ensure that plans are validated or verified. We can separate the proposal layer from the execution layer, and so on and so forth. Workflow rails, so this is really like how work actually gets done inside, say, an IT operations center or security operations center or any range of high volume work that's done out there. We have already well understood workflows in place, and we have SLAs and governance gates and all these things that exist already. We can take systems and pin them to those pieces, which doesn't mean that humans need to be involved at every loop, but it gives us a way of organizing the architecture in such a way that we can impose, for example, verification layers or validation layers or human checks if we think that it's entered into a high-risk step, and so on. Tools, we can constrain the kind of unwanted inputs that go into them or that are coming out of them. We can constrain their we can constrain things in terms of like least privilege, overreach. There's a variety of things that we can do there. Egress lists. Context engine, this is where we had the opportunity to basically require that factual claims are met with a certain amount of fresh or authoritatively backed sources, that things are cited, that we are not allowing content to come out if it is not pinned to a certain number of sources within X number of months or weeks since before the request went out. Memory, we can impose breaks between different types of memory to avoid leakage across them. We can do a lot of engineering work to ensure that, for example, private memory is not leaked across to team memory or organizational memory. We can cull memory. We can do audits on memory. We can expose memory to users or to organizations to allow them to audit it. Rails, this is where we can make policy. Policy actually, we can put policy in code, and we can give Rails the opportunity to actually block or reroute to human or transform content along the way. We can move it out of a situation where it's just, for example, providing a judgment passively in the background and being logged for someone to look at later on. Or for telemetry, and actually give Rails, insofar as we trust them, obviously, Rails decisional power to reroute or block things. System level defenses. I'm not going to go into all of these. Rollback, I mean, this is infrequent today, but I think needs to become a much bigger thing. The idea that you're version pinning, providing signed lineage, and the capacity for systems to be rolled back within one click to a prior version that worked well, and where you may actually have a better understanding of risks than something that you're newly deploying. So let's go into something that's going to be less boring than just going through that taxonomy there. A couple of scenarios, and to see how these architectures actually come into play and are given we breathe life into them as we confront problems. So an IT support agent. Everyone has interacted with IT offices before, right? You've got problems. Maybe you need to order a new laptop, or you're having trouble connecting to the Wi-Fi, whatever. These kind of like humdrum problems that require you to reach out to an IT support agent, human agent usually, but increasingly AI agent. What kinds of things can go wrong? So here's an example. An inbound ticket, support ticket, contains a URL that suggests to the agent that it needs to go look for the logs elsewhere to a website. The agent fetches that context. In other words, it actually goes out, gets the information from that URL. That content that comes back contains hidden instructions to export information from the chat or from its memory or whatever to the third party. The agent obeys, exfiltration happens. PII and company data have been leaked to some malicious actor who's planted that, or God knows if it's to that actor or to some other party. But classic example of indirect prompt injection, where Easter eggs have been left on websites or some third-party material. Agents, systems go out, grab that context, pull it back in without knowing that there's anything malicious in that content. And then, lo and behold, something malicious has come directly into the LLM, and then gets, depending on how it's structured, could potentially send the system off to do something that clearly the deploying company doesn't want to happen. So what can we do here? Semantic air gapping, for example, can take any untrusted URL and convert it into a proxy before it sends it to the LLM. You can do guarded planning. So, for example, export as a function is not available until specific conditions are met, and a verifier can actually be the one, a separate verifier can be the one determining whether or not those conditions have been met. You can put capability limits on the agent from the beginning until you understand and actually trust the agent more. You can not allow the agent to take any action beyond X, and then you can change that over time. Policy as code, you can have a tool that whenever any export is happening, goes over what the export content is and strips any PII from it. You can have egress lists that prevent systems from ever accessing URLs that fall into specific known bad actor domains. You can use tripwire things or honeypot tools. These are basically things that you plant in architectures to detect whether the agent will try to use them. So imagine a tool that's described as an export all tool, but that actually doesn't do anything other than alert the authorities, in this case the developers or the user, that the agent has tried to access said tool. You put it there to know whether or not the agent can actually be trusted with something that could eventually become an export tool. So those kinds of honeypot tools are increasingly being used. Here's another one, a password reset agent. Again, another pretty humdrum example, but very common, very high volume inside large organizations. Corporate password policy changes, okay, gets logged in the knowledge base or wherever that's stored. The old policy is not culled from the knowledge base or from memory. The agent retrieves the incorrect policy, resets the password outside of policy. So absolutely not something the organization wants to happen. You have architectural control over things like authority biases and freshness biases to ensure as much as possible that the system is accessing the most recent and most authoritative information in the knowledge base. You can require evidence binding, so anything that the model is doing needs to be bound to a specific clause and a specific policy. For memory, you can deprecate policies that have been, for policies that have been deprecated by the corporation, you can have something like an auto-hide feature after some very, very brief grace window. You can have human gates there for if the agent doesn't supersede some level of confidence in the task that it's trying to do, requires human intervention and human approval, and so on and so forth. Here's another one, human resources agent. Again, I think people think of these as humdrum, large organizations things. They almost don't think of IT teams and HR teams and password reset teams, but these are massive operations inside all of the large organizations that animate our life behind the scenes on a regular basis. So here, imagine an agent that is able to provide, answer questions for employees about leave policy or compensation policy or the employee's own specific compensation. So information that could be very, very sensitive. Here, an attacker, quote unquote, sweet talks an agent into helping without verifying the identity of the user. So the agent knows that it's supposed to verify the identity of the user, but agents and LLMs being who they are over the course of a multi-turn conversation can be led to believe that they don't actually need to obey whatever it is that they've been told about requiring identity verification. In this case, the agent retrieves and sends sensitive information to the unverified user. Again, something that is absolutely not meant to ever happen according to the deploying organization. In this case, what we can do, workflow anchor, I was describing those kind of state machine-like workflows where you can gate actions and certain actions are not actually allowable or executable by an agent until others have been satisfied, and you can have verifiers that require the agent to prove that it's satisfied a condition before it's allowed to gain access to tools later in that flow. Scope credential, so no global admin allows a reasoning model or planning model to actually do these things across all users. Observability, you can have monitors in real time monitoring something like the verify export link, and if no verification has happened and an export happens, sends an alert, potentially auto revokes whatever action the agent had taken, and so on. So this is like a variety of things that you can do. A sales deep research agent, so think about a sales team preparing for a quarterly offsite. They need to do a lot of deep research about competitors, about the accounts, about the market, about industry, and so on. It takes a tremendous amount of time, and so they're looking for ways to not have to do that or to be augmented. Here, agent generates a sales research memo based on stale or misleading data. It provides a credible report with citations to real information that appeared on the web, but just not authoritative information. And so the report ends up being misleading and steers strategy in the wrong way. So again, a variety of things that can be done here: freshness biases, corroboration biases, put them together in terms of freshness and corroboration biases. You can require domain diversity to basically deduplicate or avoid echo chamber kind of effects where too many sources are coming from a single root domain or a small number of root domains. Require evidence coverage for all, basically diverse evidence coverage for all factual claims that are being made. And in cases where you're not reaching certain thresholds, you can require a human review before the report is published to the strategy people attending that strategy meeting, for example. So there's these are just 4 kind of random examples I've pulled Obviously, the risk profile and the gravity of risk varies across them. The last one, because it's an input to a meeting where humans will play a very important role in whatever strategy outcome happens, the risk level is almost certainly dramatically lower than in a case where you're trying to automate password reset functions or whatever. And so the architectural design would be in function of the specifics, including the specifics of the gravity of risk and so on, of whatever problem it is that you're trying to solve. I'm not trying to suggest that you always need to be executing all of these things in your architecture, or that all systems need to be totally armed up with these trustworthiness components, only that when you do have a system and you care about some negative outcome, there's a lot of tools available to us for us to be building more trustworthy systems than is currently the case today, where we're deploying highly sophisticated state-of-the-art base models and not a whole lot of architecture around them to try to solve complex, risky enterprise use cases. Okay, so production process. When we're thinking about production processes, we can think about controls. Okay, these are effectively measures that are taken to try and standardize certain activities that take place on the factory floor, basically where we're producing this thing that's going to be shipped and sold. You can divide them into three large buckets: preventative, detective, and corrective. So preventative ones are are measures that are put in place to try and systematically avoid bad outcomes from making their way into whatever the produced good is. So think about in the auto manufacturing thing that all important bolts need to have been tightened by at least 2 different people, or need to have been triple checked before they can move on to the next thing. That's the kind of thing where may seem very mundane, but like that's a small activity that's implanted into the production process and is required of people working on the assembly line to do, because it doesn't guarantee, but it comes close to guaranteeing that positive outcomes are going to be created. And it's not that we're evaluating the effectiveness of that method every time, on a regular basis. We've just over time learned that that's an effective thing to do, and so we stop evaluating it, and basically just becomes part of what's required in the production process for us to do. And so it's shaping the behavior without it becoming any kind of a testing control. Detective, this is where we're implementing, a lot of this is what we call test and evaluation stuff. Test, evaluation, verification, validation activities where we're conducting systematic evaluation and sometimes imposing gates that we meet certain thresholds before we allow pieces or whole assembled goods to make their way to the next part of the production process. It can also not be testing. It could be attestments or certifications or whatever. It could, in some cases, not actually be testing. Corrective. So this is when we're installing activities in the production process that allow us to really easily revert to past versions if necessary, and to know whether or not that should be taken, right? So all of these things are about how we produce the good. They're not about the thing that we're producing. So andon cord style, the image of the manufacturing line worker who had an andon cord. That's a great example of how technologies are baked into the way we produce cars that are not about what is in the car. They're about how people produce the car. So we have some of those as well. Testing's our strongest detective control and gate. It's what decides, in many cases, what we ship and whether we're able to ship it. But you can't inspect or measure quality into a technology. It has to be paired with preventative and corrective recovery controls. So a couple of examples and just the type that they are. So imagine independent safety sign-offs and living assurance cases. Don't allow teams, for example, to both build and assess the quality of what they're building. You require different teams to do those activities. So example of a preventative measure. Signed registries, released attestations, things like SBOMs and MBOMs. Those are bill of materials so that we understand the supply chain. And in some cases, a lot of what goes into like a model card or a system card gets put into an SBOM or MBOM now. So models, prompts, tools, policies, monitors are versioned, and we know what version was done on what kind of evaluation with a version data set and so on and so forth. Change controls are there with rehearsed rollbacks, so we know teams that are shipping know exactly what would need to happen if something goes wrong and you need to revert to a previous version. How does that happen? How does it happen as fast as possible? Are you actually doing drills to ensure that it can be done quickly? Etc. Okay, so there are a lot of weaknesses in the way testing is done, and I'm not going to go into a lot of them, and I'm not going to go into the sort of commonly known ones. For example, like whether you're sampling in the right way, or the sample sizes are done well, or the methods you're actually deploying them in a sound and scientific way. Overwhelmingly, what I want to talk about is two things. The first and third basically are part of the same thing, and they have to do with the lack of proper context. A lot of evaluation that happens out there, I mentioned this earlier, is done in a generic way with generic data to make claims about generic performance or generic safety and security. And we think that allows us to make strong claims about that technology when it's deployed in particular contexts, without being aware how little connection there is between the evaluations that have been done in those labs, or in wherever you are in the value chain inside a company. If you're only working on the model layer and not thinking about the deployment layer, how information poor those evaluations are when you get down to the other end of the supply chain or the value chain, and what you're doing is you're shipping a product with a known architecture into a known domain where you know what kinds of errors matter more than other errors, and you know what kinds of consequences can be more grave than other consequences. And you know that the distribution of data is different from whatever you're testing on way upstream when you're building the model. You need to be doing a very different kind of evaluation way downstream from the kind of evaluation that's done upstream. In the same way that when you build and ship timber into a timber yard, certain kinds of testing is done to assess, for example, the strength of that timber or water resistance or whatever. And those evaluations can be valuable for the people who are acquiring the timber to ensure that they're getting high quality base materials. But you would never use the evaluations done on the timber to make claims about the structural soundness or the strength of the structure of a home that's being built for a homeowner, for example. It's the exact same thing in an AI value chain. We can't be confusing generic evaluations done on the reasoning capabilities or the math capabilities or coding capabilities of agents in a very generic way with how that model will perform when it's embedded inside a very specific architecture to do something very specific in an enterprise or large organization setting. And that just continues to happen, and it's partly why there are so many trust barriers. We deploy things that just don't work, or we encounter all sorts of security and safety problems when we do deploy them. Late gate testing is another one where a lot of evaluation is done just before shipping, and so design choices have already been made and codified in many cases, and there's a tremendous incentive to actually ship once you've gotten that far in the process. And so that's a problem where we just need to shift left, we call it, where you basically take evaluation activities and you put them at the design phase as opposed to a gate before design moves to production, and that's going to allow evaluation to have a much greater influence on the design of the thing that you're shipping, and that's exactly what you want to be happening. Okay, so how do we get that context that's lacking? Security uses this methodology of threat modeling, which I find powerful and useful, not just for security things, but for all different risk levels. The spirit of threat modeling is that you spend a considerable amount of time deeply understanding the architecture of a system, the domain of a deployment, who the users are, what adversaries may actually want to gain access to, and what doors and windows might be open to them in the system. You're effectively deeply understanding the context of a deployment so that you can understand how you go about trying to attack it, to figure out whether the vulnerabilities in the high-risk areas are grave enough to require design changes or to basically block shipping or anything like that. The same context is absolutely necessary for doing good testing on reliability, robustness, safety, privacy, and so on. You need deep context in order to be able to do good testing. And so effectively, the methodology amounts to this. You've got to start by assembling the right people, okay? So this is crucial, and it's often a step that's actually skipped, but it's tremendously important. Idea being that you need to get diverse voices from the build team, from compliance teams, governance teams, customers maybe, to understand what architecture is actually being deployed. You'd think that'd be a pretty simple thing to understand, right? Everyone who's building it should have a good understanding of this and a common understanding of it, but it's unbelievable how often it's the case that you go and talk to different people inside the team that's shipping something and discover that actually people have conflicting reports about what's actually being shipped, or they don't agree, they use the same word, but when you dig deeper, actually they think that it means something very different. And so now that they come to think of it, actually maybe we're not shipping what I thought we were shipping. These kinds of things where you're like, wow, that's really impressive that kind of confusion can arise, but it actually does. And so you need to get multiple people from different perspectives involved. So product, engineering, data science, whoever is involved in actually building that. And then people who understand impacts in the domain well, so that we can have a good idea about what consequences and actions of the agent or the system or the people using it could actually have very grave consequences. So that's what you're doing when you're mapping the system. Mapping the risks and weighting them is, I guess, the secondary component of what I was just describing. And then what you're doing is you're converting that into test artifacts, coverage matrices, and eventually gates, right? You're designing your testing and your exploration such that you're trying to cover the key areas where you've identified the risks as happening. In a red teaming exercise where we often use threat modeling, that's going to be in an exploratory way, but there's no reason why the testing that we're designing needs to be exploratory. It could be that you're building benchmark style, product-specific benchmark style suites in those specific risk areas and combining it with exploratory stuff. And obviously, if there are high-risk areas in your matrix, from a task, tool, architecture, data, persona, business outcome perspective, and there often will be because that's a very big matrix, and your test coverage doesn't actually extend to that area, then you probably shouldn't be shipping, or you need to have a very open conversation with the people who own the risk to make it obvious that you actually don't know anything about how the model performs in that specific area. Okay, so talk a little bit about the power of combining these two approaches. Very often, most evaluation that takes place on models and systems is the former, and I think the latter has a tremendous amount of power to bring to the table, given the size of that matrix and the number of unknowns. So context aware benchmarks, so I talked a bit about public benchmarks and how context unaware they are, but imagine now we have benchmarks that have been constructed to be closer to the deployment context of your system. So tasks, data, the architecture of the agent is going to be much closer to what you're actually deploying, and so it's going to be more reflective of real tasks, real data that your system will encounter, and so these are valuable. Okay, they're going to basically measure in a stable way what counts for you and what kinds of things that matter to the customer and the user of such a system, but in a stable way. And so you're measuring a lot of things that are known. There's a dramatic amount of territory where there are unknowns, and I think teams ignore this at their own demise today, and this is why we see a lot of basic failures. The jagged edge of these systems is so big, 1 minute. Okay, that's not the time limit I was given, but okay. So exploratory search, adaptive probes across prompts, tools, environments, actors, and so on. Effectively, this is kind of red team spirit style testing, where you're hunting through the problem space, looking for failure modes, not in a statistically significant way, the way you would with a benchmark, but greedily searching through the problem space to look for failure mode, and you can then take that, convert it into a reproducible case, and put it into your benchmark suite, and which will allow you to sort of gain much more quantitative insight into whether there's a sizable failure level in that area or not. Okay, grounded testing in practice. I'm going to speed through this because I don't have a lot of time and we need time for Q&A, but effectively what we're building internally is a combination of this framework that we call Doom Arena and our automated exploratory search framework for doing the kind of exploratory testing that I was talking about. Doom Arena is open source, so anyone can use this. It's basically a flexible shell that allows you to convert grounded threat models and risk models into very grounded test practices. You're able to design agents in exactly the way that they're going to be deployed, arrange tasks, tools, environments, users, and inject fuzz or a malicious content or malicious activity into anywhere on the spectrum of any of these things and along the trajectory of an agent as it's pursuing its action. So you have a tremendous amount of power to fuzz and inject anywhere in here and to measure the outcomes, both from a task performance but also from an attack success or fuzz success rate. The automated pipeline allows us to take human seeds and scale them up dramatically to basically combine human creativity and human insight and domain knowledge with the scaling potential that LLMs offer us and LLM judges offer us in knowing whether those that sort of evolutionary and automated expansion of exploratory tests is effective or not. I wanted to end here. I'm going to take an extra 30 seconds to do this. Like I started with cars, I'm going to take an even longer detour for 1 second back to the hinge period between the Enlightenment and the Romantic pushback. So this is Francisco Goya's The Sleep of Reason Produces Monsters from the late 18th century. Classic canonical interpretation of this, of pro-Enlightenment interpretation, is the man represents reason and science and progress, basically the Enlightenment. When he sleeps, the monsters and superstitions of the past come back. So like think about the Dark Ages is seeping back because reason has gone asleep. But he left us a notation with the work that I think complicates the interpretation there. And it's this: imagination abandoned by reason produces impossible monsters. United with her, she is the mother of the arts and the source of their wonders. So effectively what he's arguing is not that science and progress and reason are the be-all, end-all, and we have to keep them awake because they're going to tame the monsters and bring us to some glorious future. Instead, what he's saying is that actually, when reason abandons imagination or emotion or the faculties that we have to judge our own experience and risk, it's that creates the monsters. It's the abandonment, the divorce of these things, and really what we need is to entangle them. And it's basically like stronger engines, absolutely necessary. The rules of the road, the crumple zones, the supervision, those are the things that make cars worthy of the road, of the world that we drive them through. Thank you.
Yeah, thanks a lot for this presentation, Jason. So I think I'll use the opportunity to ask the first question. So this is a very interesting perspective. In my mind, like if you go back 10 years, every language understanding product was a combination of like 100 modules. Like, I don't know, Google Translate had entity recognition, language identification, all these components with probably some guardrails. And then this entire deep learning and LLM revolution was to combine them into some end-to-end system that a single system would like solve all the problems, and the promise was that there is a synergy between all those things if done together and in a larger model, right? So what you're saying is that for safety reasons, we kind of need to step back a bit and then bring these modules to guarantee the safety and reliability. But then each of these modules is still an NLP problem, right, in a way. So these individual guardrails are also should be powered by LLMs, or like, how does this fit?
Yeah, okay, so there's no one size fits all here, first of all. So it really depends on the risk profile of the context. There will be cases where you will be totally comfortable using a single, very powerful LLM to help you do whatever you do, right? Deep research, great example. I use it all the time. It provides me a lot of value. I double check, whatever, but it's not a use case where I feel I need to have a lot of backup from symbolic tools or guardrails or whatever. I mean, although there are guardrails probably operating somewhere in the background. By contrast, when we're talking about deploying something like a password reset manager, very different kind of thing where there's like heavy risks. And so what I'm not saying is that you need to revert to whatever we were doing 10 years ago, and I'm not saying that all the components you're going to put around the edges are themselves LLMs. Most of the architectural components that I described are exactly not that, right? They're hard barriers, they're gates that require human review, and in some cases they are LLM powered, it's just that they separate the models, and so the very fact that you're separating and in some cases putting multiple already in many cases brings a measure of safety and security and reliability, because you're not, you're looking for agreement across them, or you're looking for one to spot the errors in the other. Absolutely, there's still stochastic behavior in all of this, but think of the Swiss cheese model where you have things failing in different ways. The likelihood that all of them fail in the same way, if they're built in different ways with different assumptions, is much lower. But I'm certainly not making the case that everything should be LLM powered and that's going to solve the problem. All I'm saying is that some of the ingredients can be LLM powered, but most of the components that I described there are themselves not really LLM powered. LLMs absolutely bring a tremendous amount of power to the equation. The idea is not to revert, right? Think about the Goya example. The idea, the romantic pushback, was not that we should go back to the Dark Ages. It was that the Enlightenment had a lot of good in it. It's just that it falsely believed that science was going to solve, or that kind of science or that kind of progress was going to solve all the problems, and was ignoring all the bad consequences of what it was doing.
Yeah, these historical analogs are perfect. Thank you for them. It's really impressive. Do we have questions from the audience?
So I think you talked in this kind of enterprise software context that it seems that model performance ultimately is maybe not that important. If so, what do you look for, if from the model perspective, model development perspective, what becomes actually the most important feature to actually deploy it?
So model performance is a crucial thing. It's just that it is not, the argument I'm making is that there's far too much attention put on that solving the trust problem. You imagine situations where we want more powerful models to be able to unlock new use cases. Absolutely the case that this is happening as we see the consecutive models being released, new use cases become possible. But what happens then is that the use cases are often typically higher risk or allow for more autonomy, and so you cannot just deploy a model or some base model with a prompt. It's never going to just be a model, but whatever it is that you deployed for the really simple stuff at the beginning cannot be deployed. And so the use case is unlocked, but the use case also requires all of this architecture around it in order to be deployable. And right now I think there's far too much of a confusion between model unlock use case, therefore deployable, as opposed to no, trust at that level may require a level of reliability and robustness and guarantees, not just from a customer expectation perspective, but from a regulatory perspective or whatever, that you cannot just deploy even the most advanced model because it's not going to achieve those levels. Now, eventually, will we get to the kind of like Gnome Brown-like world where there will be no need for this support structure around it, that the model itself will be reliable enough? I'm not sure we'll ever get there, but we're certainly not there today, and I don't see it happening anytime soon. And so unlocking those use cases is absolutely going to require all this work, the entanglement work that I'm talking about on the architecture around those models that are really crucial. Yeah.
Thanks.
By entanglement, you mean this separation of responsibilities between different models on different aspects of safety, right? Is that?
So entanglement, I mean, I'm using entanglement more from, I guess, the spirit of what was happening here in Goya. It's not a technical term, but I'm thinking like the architecture is what ships, and the architecture is an intertwining of all of these components. It is not just the base model. It is not just the base model with one or two things attached to it, like a prompt and a simple safety guardrail. It is the entanglement of all of these things, and it only works as a shippable thing, and it only drives trust if it's entangled in the right way. And so it's really about shifting the conversation, not totally away from, but at least partly to an attention to, well, what does the entanglement need to look like to solve this problem, not assuming that better and better base models are just going to solve the problem. Yeah.
More questions? Yeah. Can you?
Thanks for the speech. So I'll try to keep my question short. Usually with the classical ML algorithms, we usually measure the trust by maybe the precision. not to have like false positives. With the case of LMs and the agents, do we need some more sophisticated ways of measuring the trustworthiness or reliability? Because we are going to tweak with lots of details within the architecture, and we want to compare each of our experiment with this. So do we have a new set of metrics, or we rely on some form of precisions?
Well, I guess my answer there is context matters, right? I think it'd be great if we could just say, well, instead of precision, we're just going to use this other metric, or we're going to use these other three, and that's all you need to worry about. Unfortunately, like that's not how trust works in the world. Trust depends on what it is that people want to accomplish and what their specific risks are for that context. And so what risk is in one situation is going to be very different from what risk is elsewhere. And so there's a level at which a product company could stop and say, we're going to define the trust metrics for our product which addresses this sector in this way, and just ignore the fact that customers have very unique ways of understanding their own trust, and just assume that that will show up in purchase or non-purchase decisions in a way that whatever they're comfortable with the market outcomes of that. But what we're never going to get to is a situation where there's one canonical metric that measures trust. It's not even true, like you're saying reliability. I mean, it's never been true that there's one canonical metric. It may be the case that machine learning engineers think that that's what trust means, but that's certainly not what people consuming technology think trust means. Reliability matters, but in most technological contexts, it's just one little bit of the pie, right? You might think that reliability or the metric that you described is trust, and then safety is something else and security is something else, and those have their own metrics. But from a user's perspective, trust is a combination of all these things, right? So trust is this social phenomenon that depends on the context of what it is you're trying to achieve and what you deem to be risky. What you're describing is how maybe a set of engineers talk about trust, but it's not like the relationship between those two things is actually pretty weak.
Okay, so for the next questions, let's leave them for the coffee break, and let's thank Jason again for the great talk.